Hey guys, so IB Math semester 3, almost there, quarter 2, week 2. So today's topic is going to be about, really it's an intro to calculus. Okay, so you can just put a big fat in your notebook. Calculus. Okay, pretty calculus. You get the idea. And so I want to start off with pretty much very, very basic concept. So, so there's two branches of calculus. There's differentiation and then there is integration. These are the two branches. Differentiation and integration. We're going to talk about differentiation first. But it is important to know that just like adding and subtracting, multiplying and dividing exponents and roots. Okay, just how all of these are opposites, they're called inverses, right? They undo each other. So just like adding and subtracting undo each other, multiplying and dividing, and then exponents undo each other. So just like there's an opposite relationship between these three pairs, differentiation and integration are opposites. Differentiation and integration are opposites. They undo each other. All right, and so we're going to focus on derivatives first. We're going to focus on differentiation, which is the process of finding derivatives. Okay. All right, so without further ado, what is a derivative? What's a derivative? What's a derivative, guys? So to answer that question, let me actually go back to Algebra 1 and something we are all very, very comfortable and familiar with, and that is the concept of slope. So with something like slope, so this is your coordinate plane, and say you have a line, it goes like this. And the formula is something mx plus b. So m is known as your slope, right? Slope, aka you should also know it as a rate of change. Well, you might not know, you may have heard of it before. Slope is really actually, it is with linear equations, with something linear like this. Because you've never really heard slope when it comes to a quadratic. There's no such thing, or a cubic, or anything like that. So with slope, that when we're talking about slope traditionally with linear equations, okay, not only is slope a rate of change, but it is a constant, I don't want to say unchanging, constant rate of change. Okay, and so what I mean by that is this. I know it sounds kind of weird to hear the words constant and then change in the same sentence, but I'm gonna show you what I mean by that. So say I have a coordinate plane, okay, and say this is my graph. Na-na-na. Na-na. Na-na. Okay, 4 points. Make these prominent so you guys can see. So let's identify the slope. Let's find the slope here. But just for fun, just for funsies. Funsies. Yay, funsies. Okay. Really, really simple. Okay, so rise over run. Rise over run. So let's pick these 2 points. So I went 1, 2, I went 3 up. So I went 3 up. And then I went 1 to the right. So positive 3 over positive 1. That gives me a slope. My slope is 3. And what is so crucial about linear equations and slope is that no matter where you start and where you end, it's always going to be 3. 3 over 1, 3 over 1, 3 over 1. Just to really show you. 6 over 2, which is 3 over 1. 6 over 2, which is 3 over 1. So that's what I mean by constant. It is unchanging across the board for linear equations. The slope does not change. It is the same no matter where you are with linear equations. Okay. Now, that is common knowledge. Okay. Now, let's consider a curve. Any curve. It's a nice straight line. Another nice straight line. Okay. Coordinate plane, and say your graph looks like a parabola. Not a parabola. Well, yeah, a parabola. A nice parabola. Alrighty. So all a derivative is you can think of a derivative as, well, I'll show you first, and then I'll write it in words. So say I picked, let's zoom in a little. Zoom. Okay. say I pick these 2 points, or this point and this point. Okay, just connecting these lines, that is the, you know, I don't want to call it the slope. Yeah, we could call it, I guess just for now, we'll call it the slope. That's the slope connecting those 2 points that I chose, that one and that one. Except what happens when we choose 2 different points, say here and here? Well, the line changes. And again, let's say if we chose here and there. Again, I connect them. Ew, it's horrifying. Again, I connect them. Notice what happens. At every slice, go around. At every slice on this parabola, on the red parabola, in the green here, and the blue, the 2 points I chose in blue, and then the 2 points I chose in purple, the rate of change with curves is changing. Okay? Notice these lines are all vast. They're very different from each other. They all have they're all different, like, levels of steepness. Okay? So you could think of, let me zoom back out. So with curves, guys, so we know how to find the rate of change with straight lines, with linear equations. It's just rise over run. But when we're talking about anything that has a curve, okay, the rate of change is different depending on where you land or what points you choose on that graph. So whatever slice you choose on whatever curve, so like this one, for example, like that point and that point, just connecting the two. Very close. Sorry. Let's do another one. Let's do that one and that one. Connect those two. Let's do black. Let's do this point and this point. Oops. Guys, so please note just the different, like, levels of, like, how steep something is, how steep these lines are. They're all varied. They're all different. So, I'm going to say it again. With curves, with anything that has a curve to it, the rate of change is different depending on where you land on the curve. Okay, so you want to call, really the technical term is instantaneous. Instantaneous rate of change. All right, aka derivatives. All right. Differentiation. That's where we get that word from. Differentiation. The rate of change differs no matter, like, depending on where you land on that curve. Okay, so let's do power rule. Let's do the power rule. This is called the power property. power rule of differentiation. This is simple differentiation. There are more that we're going to discuss, but the power rule is the most iconic. Okay, I do want to start with that one. And so it's a very, very simple law. If I would turn the page. Here we go. Rate of change, I don't want that. Limits, it's not what I want. No. Here we go. Simple differentiation. Where is it? All right. F of x. So say you have a function, x to the n power. Very standard. So, for example, say you have a function that looks like this, x to the 3, x to the third power. All right, so the power property, the power rule of derivatives, it tells you what to do. It tells you this. I'm going to write it out first. Let me actually. Oh my gosh. Okay, this notation, this left-hand side right here, this is known as, just for your information, this is notation for the first derivative. So there are second derivatives, third derivatives, fourth derivatives. And you would just add however many dashes that you want. But I want you to focus on the first derivative, at least for now. Okay, so let me erase that actually. All right, so this is your power property. This is your original function right here. F of x equals x to whatever n power. So this is the power property tells us. It tells us to first pull it into the front. Okay, it tells you to whatever exponent this is, pull it down here into the front, and then subtract 1 from the original exponent. Okay, so it seems kind of weird, like, before we get to the actual examples. So here we go. So example 1. Say I have a function f of x equals x to the 4th power. So in this case, my n would equal 4. Okay, very, very quickly. Really, it's pretty harmless. The derivative, it tells me to find the first derivative. So the first derivative, that's a dash, it's not a 1. It tells me to put the exponent in the front. Keep the variable x, and then it tells me subtract 1 from the original exponent. So my final answer, f prime, I'll note that's when you say it, it's prime, f prime of x. So the derivative, the first derivative of this function, x to the 4th, this is the original function, is 4x to the 3rd. And that's it. That is the power rule. We'll do 2 or 3 more examples. Make sure you have it. Example 2. Say I have a function f of x equals, let's say x to the 5th. Okay, so I'm just writing the power rule. So f prime of x, whenever we're talking about x to the 5th, if that's your function, remember the first thing, you put the exponent in front. So right now, there's a 1 right there, an invisible 1. So really, you're actually multiplying the exponent and whatever coefficient is here. So 5 times 1 will be 5. Okay, and you'll see other like coefficients there in the future examples. But for now, so I have 5, and we're not done yet, x. And now don't forget we have to subtract 1 from the original exponent, so that's 4. So that's your final answer. Okay, it's pretty harmless. People hear calculus and they just have like total freakouts. Example 3. Don't let math scare you. Say I have a function and it is 4x to the 7th power. Alrighty. So again, it tells me to find f prime of x, aka the derivative. Find the derivative of the function x. So first thing I do, I'm going to take this exponent, multiply it by this coefficient. This time I can see the coefficient. It's a 4. So I'm going to multiply it by the coefficient. So 7 times 4 is 28. So f prime of x, write it out. So 4 times 7 is 28. Keep that x. And then don't forget we have to subtract 1 from the exponent. 7 minus 1 is 6. This is my first derivative. I think they're kind of fun. Like, I know you guys might not think so, but I think they're fun. Okay, let's do another one just for kicks, just for funsies. Go back. Okay, here we go. Just for funsies, where are we on? Example 5? Wait, example 4? Yeah, example 4. Say I have a function, f of x, and it goes like this. 1/2 x to the 10th power. Okay. So f prime of x. Again, this is your coefficient. Treat it like a number. So 10, multiply it by that coefficient. 10 times 1/2, aka 10 divided by 2, is 5. Keep that x. Now, don't forget, last step, we subtract 1 from the original exponent. 10 minus 1 is 9. See how easy, guys? Simple. So let's do one that involves square roots now. Example 5, square root example. So you should already know from the laws of exponents week, little blast from the past. you should have in your brain that the square root of all right. This is very essential. Okay. The square root of x, so it could be I'm sorry, not square root. All right. So n is the whatever, it could be whatever number, okay? Not just 2, it can be, so that's a square root. That's a cube root. So whatever number is here, it actually goes here as in the denominator. This relationship is extremely crucial. You will especially need to know it and be comfortable with it and be able to use it fluently in when finding derivatives that involve square roots. And we're going to do an example right now. Okay, so just so you know, just so you have it written out. Say you have this square root x, this square root. Okay, aka sometimes it'll be written just like this. This is how you see it most often. It's just a square root with no number here. Okay, so aka, where is it? Here it is. These two are also known as x to the 1/2 power. So square roots and exponents as fractions, okay, 1/2 as the exponent. So the fraction exponent. Let me do another one. So say I have the cube root of y, right? So then in reality, if you want to get rid of that square root, but you want to preserve the integrity of whatever this is saying, it would be y raised to the 1/3. So whatever number this is actually the denominator. Okay, without further ado, let's do an example that involves differentiation and square roots. Alrighty, differentiation and square roots. But in my example 5 now, say my function is, let me find a good one. Sorry, I didn't know I was switching back and forth. Aha, that's a good one. 6, oopsie, 6 square root of x. And I want you to find f prime. I want you to find the first derivative. So first thing I want to do, I want to rewrite this because I need an exponent to work with. That's like the entire concept of the power rule, is it involves a power. Okay, but I don't see a power right now, but I can easily rewrite it to where I can, a power will, like I'll express it using an exponent. And then I can use it. Then I can manipulate it. Then I can solve it. Okay, so based on the little review we just did up here, so really this problem, I'm just going to rewrite the problem. F of x, really it's 6 times x to the 1/2. All right. Now, but this is, now I see an exponent. I see an exponent and I can work with it, okay? Because now I know what to do. I can multiply the exponent and the coefficient, 6 times 1/2. And now let's get rolling. 6 times 1/2 is 3. Keep that x. Now 1/2 minus, don't forget to subtract 1. So I can rewrite it, just for simplicity's sake, to keep everything. F prime of x equals 3x raised to the negative 1/2. Okay, this is technically the right answer. But what I want for you guys to do is get accustomed to always eliminating negative exponents. No one wants to see that. So we're going to go to the next page, and we're going to rewrite this in the box. We're going to do a little shuffling just to get rid of that negative exponent. So we said this was what we have. 3x to the negative 1/2. So 3x to the, so I can I don't know if you guys remember, to eliminate a negative exponent, you can just move it downstairs. Move it downstairs. Okay, that eliminates negative exponents. So my final answer is 3 over x to the 1/2, aka even nicer looking, 3 over square root of x. And then you're done. That kind of seemed like a lot, but not really. And so let's do 2 more, and then I'll leave you guys alone. 2 more, guys. Oops. Okay, what example am I on? Number 6. Ouch. Okay. Example 6. Say I have a function f of x, and I have x cubed plus x squared plus x. So 3 terms, x cubed, x squared, and x. So I'm going to apply the power property, the power rule, independently on each term. Okay, so without further ado, x3, really that's just 3x squared. X squared, the derivative of x squared, remember, bring it to the front, subtract 1, that's just 2x. Okay, and last one, x. It looks like the easiest, but x. Isn't that really just... Let me make it black, actually. Actually, no, let me keep it red. So that's your term. But isn't that really just x to the 1 power? And also, isn't there another invisible 1 in front? So now let's follow the power rule, just like normal, just like we've been doing. Remember, we multiply this exponent with the coefficient. So following that, we get 1. All right. Keep the x there, just like normal. And now don't forget we subtract 1 from the original exponent. So now I have x to the 0. But if you remember, anything raised to the 0 power is 1. So don't I actually have 1 times 1? And isn't that just 1? So, kind of, not really complicated, but there is a process to, like, showing you why the derivative of just x all alone, really just ends up becoming 1. All right, so now I have my 3 parts. I'm going to put them all together. Ooh, excuse me. So, let me make it. All right, that's the third derivative. So, f prime of x, let me actually put them side by side. So I'm going to rewrite it. F of x equals x, this is the original problem, plus x squared plus x. So f prime of x is 3x squared in the green, 2x in the blue, and then x, the x's derivative, remember we said was just 1. There you go. And so whenever you see multiple terms in the same function, in the same equation, or whatever, then you would just treat every term individually. Okay, let's do one last one, and then I'll leave you guys alone. Let's do, what is it, example 7 now? F of x equals x squared plus 3x minus 5. So again, we have 3 different terms. And you're going to see how each piece plays out. So power property to every term individually. So x squared, remember there's that invisible 1 there. So 1 times 2 is, so that's 2. Keep that x there, and 2 minus 1 is 1. So really that's just 2x. And now we're going to take this piece, 3x. Isn't that really just 3x to the 1 power? And so we multiply, just like we've been doing, multiply the exponent and the coefficient to give you 3. Keep that x there. Don't forget to subtract 1 from the original exponent. But really, isn't that just 3 times 1, which is 3? Because anything to the 0 power is 1. Last piece, we have negative 5. Now let's talk about negative 5. Isn't negative 5, isn't there, can you imagine there's an x to the 0, an invisible x to the 0 right there? So, and we can do that because x to the 0 is equivalent to 1. So we can put an imaginary x to the 0 there if we want to. Okay. So now that we, I don't know why I erased that. Now that we have that, we're going to follow the power rule just like exactly like we've been doing. Multiplying the exponent with the coefficient and then subtracting the original exponent, 1 from the original exponent. So just like normal, let's just pretend everything's normal. 0 times negative 5. Isn't that 0? So let's just keep going, just for fun. Let's see what happens. Keep that x there, just like normal. And then, so don't forget, we have to subtract 1 from the original exponent. That gives me negative 1, the negative 1 power. But let's stop right here, because isn't anything times 0 0? So really, it doesn't matter what this is. We've got 0 in front. So anything times 0 is 0, guys. 0. 0. All right? So that anytime you see a number just like that with no variables attached to it, and it tells you to find the derivative of just a number, your answer is 0. Very crucial. That's called the constant property. Constant. That's the constant property. Okay, the derivative, I'm going to write it down. The derivative of, the derivative of any number with no variables attached to it. The derivative of any number with no variables attached to it. So, for example, 5, -3, 20, 100. The derivative of any of these regular looking numbers is always 0. That's the constant property. So going back to our problem. So this is the original problem. I'll just rewrite it so you guys can see it side by side. So what did it say? X squared plus 3x minus 5. That's the original problem, right? Yeah. Okay. That's the original problem. And so without further ado, f prime of x, the first derivative, is 2x plus 3. Really, it's plus 0. So really, all it is 2x plus 3. And you're done. And that's really it for this week. At least for simple differentiation. Next week, I am going to, I might do, next week I'll cover different properties, different laws. But for this week, I just want you to focus on the power rule of differentiation, and I'm going to post some practice problems or some problems for you to complete by Sunday evening. And, guys, as always, just email me if you have any questions. I will put the text away in the class group chat. And that's it, guys. So thank you so much for watching, and I'll see you guys later.